which I know helps. It helps with weather when weather starts getting crappy. Although now we're into spring. Although it did sleet last night. If you guys noticed, I don't know if anybody else did. My son went out and he gathered a pot of sleet to decide how much it would melt down to. Sleet is half water. We discovered in Oregon. At least the sleet from last night, very heavy, half water. We put 8 quarts of sleet into a bucket. Melted it down, put it on Facebook. I asked my friends, how much you think? How much water do you think? How much water do you think? People said 2 cups for 8 quarts, which actually makes sense if you're thinking about snow. Like if you were to melt snow, and anybody ever do this? Melt snow into a pot to see how much water is actually in it? You ever do that? It's crazy. Okay, well, forget this for a second. I'll get this back to you in a second. Snow. How many skiers we got? Mountaineers? People like to be outside in the snow? Yeah, right. Why is it so important to carry water with you while you're up in the mountains? You got snow all around you. Why is it so important to carry water? Give me one reason.
Stay hydrated.
You stay hydrated. We got snow all around. You stick your face in the snow.
Well, yeah, but cells aren't going to take the cold water as fast as room temperature water.
I don't know about that. That's a third reason he said the cells aren't going to take. Well, it won't be room temperature though. It's in a backpack.
Okay.
It'll be roughly the air, but it will be warmer than the snow, obviously, because it's not frozen. Right. Good. So the cellular level. I didn't know that. Thank you. Tell me your name.
Aaron.
Aaron, thank you. Teaching me something today. Very good. Why else? Why else can we just please?
It takes more energy to melt the snow to drink than the water that you get.
On a body level, is this cellular level as well? Like your body? Okay, I mean, I'm thinking as if you could put it on a stove and melt it very efficiently.
Oh, yeah.
It wouldn't require any energy. But you're talking about actually putting it into your stove. We've got the physiological kind of argument. Tell me your name?
Chad.
Chad, thank you. Good. I was thinking there's not a whole lot of water in snow. I mean, you stick your face in the snow and you take a big, and you get maybe a tablespoon of water. I mean, and if you've ever done this, I encourage you next winter or next week, depending on, it's bad, it might snow next week. Next time we get a nice big dump of snow like that one we had in February, 2.5 feet of snow in one day, just take a pot outside, scoop it up and put it on your stove. And then come back after it's warmed up. And you'll be amazed, maybe you won't be if you know the trick, but you'll be amazed how little water is actually in there. There's precious little water in snow. Now, of course, Cascade crud, which we often get in the mountains, is much heavier, much more dense. But the sleet caught me off guard last night. Half of what was in that pot turned to water, which is, I mean, it doesn't surprise anybody when you realize that it turned to rain about 10 minutes after. But my son was already forgotten about the outside. He was focused on the pot on the stove at that point. So, fun little science experiments. Fun little science. Then it got into a great discussion about sphere packing, like when you take a bunch of ball bearings and throw them into a container. How do they lay down? And that has ramifications for when you're talking about going hiking in the mountains. Everybody try to hike up Scree. Or in other words, go hiking at Smith Rock. You walk up a hill, and you hit that rubble, and what happens? Very often, 1 step forward, 2 steps back. You start sliding backwards, and those rocks tend to have like a natural resting angle they fall at. And it's interesting. All that ties together. Ties back to snow. Ties back to sleet. I want to know how many bottles are going to fit in this room. How big is this bottle? It's my head for reference. How big is the bottle? Say that again.
No.
Not as big as my head? Okay, thank you. Okay, so we got about a foot this way. How about that? What do you want to call that? If that's a foot.
3 inches?
Maybe 2? 2 or 3? What do you think?
2.5.
2.5? Okay. So what's the volume? What's the volume of the bottle? Let's put this up for a second. This is fun. I wasn't planning on doing this today. We'll get to what we have to do today. So what's the volume of that bottle? So if we have a height of 12 inches, and we've got a diameter on the base. Diameter. What do we say it was? Forgot already. 2.5? Yeah, we'll call it 2.5. I like that. What's the volume of the bottle? In cubic inches. I mean, we can look at the bottom. It's going to tell us 12 ounces, 16 ounces, or 24 ounces. Sorry. I'm thinking fluid. I think it's... So what would the volume be? Call it a cylinder. Make life easy for yourself. If that was a cylinder, what would the volume be? Anybody remember the volume of a cylinder? In Nalgene? Okay, think back to geometry class. I know it was awful, it was a long time ago, you probably hated it. But this is the kind of thing that comes in handy. You'll see in one of your projects you'll do later in the course. I used this idea to help my son figure out what size pump we needed to put in a tadpole pond. We took a Nalgene bottle, stuck a garden hose in it, had him time how long it took the water to fill. And based on that measurement and how big the Nalgene was, we could figure out, go to the hardware store and get a 400-gallon-per-hour pump based on a couple quick measurements. So don't start thinking about geometry as this awful thing that's all these formulas you have to remember. how many dimensions is volume? Because when I asked you what would 80,000 of these look like, right? 80,000 of these look like. What you're thinking about is, imagine them in this room. Would they be just along this front wall? No, well, where would they go? They'd be in the front wall and then
All the way
out towards you. So if it was good and up, so if it's just on the front wall, it's left and right and up and down. How many dimensions is that? Well, left and right is one dimension. This way is one dimension. Up and down is a second, so that's two dimensions, like what you write on a piece of paper. And then coming out this way becomes three. So anytime you're talking about volume of anything, whether it's a cylinder, whether it's a cube, whether it's your backpack, whether it's that bottle, there's three dimensions you have to talk about. There's three dimensions you have to talk about. Fair enough? Fair enough? So what would the three dimensions be here? What do you think? Give me one of them.
top to bottom.
So this way around? Good, good. What would we call that? Circumference. Like that. Good.
Perfect.
Circumference, there's one. What would another one be? Height. Good. What would the third one be? What's width? Oh, okay, so this right here? So we'll call that diameter, I guess. So here's a question. You guys have named three things beautifully, by the way. We can ignore one and use one twice because of the shape. Which one can we use twice because of the shape? This is going all the way back to geometry class now. I'm being a bastard. Tell me your name. Michelle, go ahead. Which one? Good! Because think back, go back now. Circles, right? If you have to figure out how much stuff fits inside of this, that's the volume of that, correct? If you're talking about the circumference of this, or the diameter of that, you haven't described the entire circle down here, right? You've only described part of the circle, the distance around it. So you have to somehow talk about this entire area of this circle. Now you could do it with either the circumference or the diameter, but Michelle went right to the diameter, and I think most students would too. Actually, most students would probably go to the radius. Tell me what's on your mind back there.
I was just saying that the radius times squared times the height.
That's beautiful. That's absolutely beautiful. You're making it easier for us. Tell me your name.
Greg?
Greg?
Greg.
Grant, thank you. Radius squared times the height. If that thing were a box, it's a damn circle. Do you want to pretend it's a box to make life easy? No? Make it hard? Okay, that's fine. That's good. I like that. That's good. That's good. I like that. So, now, if that's the case, Grant's going with the radius squared times the height. The problem is it's a circle, and there's a really, really fun little constant that has to do with circles. You might remember called pi. Remember that guy? Good. Say that again.
Pi times radius.
Times radius again.
Okay.
If anybody's interested in why that is the area of a circle, we'll get to it eventually as we go through this class. It's kind of ingrained in this class. Like I said, I wasn't planning on jumping right into this today, but what the hell, why not? So the area of this circle is going to be that magical number pi, which is not really magical, it's actually a consequence of mathematics, times the radius times the radius times the radius squared. Yes. So the radius is going to be what? 1.25 inches, I think, we're doing my math right. 1.25 inches times 1.25 inches. I put that in parentheses, I guess. And there you've got two of your dimensions right there, don't you? Inch times inch gives you square inches. Anybody got a, oh, what the hell, let's do it together. Let's do it together here. Let's get a quick number for that. One of the beautiful things about Google, you can type mathematics directly into the Google search bar, and it will do the math for you, which is fantastic. 1.25 times 1.25 times pi. Oops, that's not a times. That's a dollar sign. Or a pound sign. Hashtag pi. Boom! Let's call that 5, shall we? Just to make life easy. 5 square inches. Can you catch the square inches? It's not just 5. I know it looks like it's just 5 there, but there are units. Pi doesn't have any units. It's a beautiful ratio. But that's an inch, and that's an inch, multiplied together makes square inches. If that sounds like complete Latin to you, I built an entire project around that. You'll do it in this class. Because that's the kind of thing I think that math students lack in algebra-based curricula is they don't understand units anymore. Like how big a trillion is, how big a billion is, how many 1,000 is, and things like that. So I built a whole project around that. We'll get to it eventually here. But right now, the area of that bad boy is about 5 square inches. Okay, I forgot to work an H. That's an H too already. Okay, good. Now Grant, you said radius squared times height. Essentially, if you ever have to find the volume of anything, whether it's how many M&Ms will fit in this room, whether it's how many gallons of paint it takes to, that's actually more like area than volume. It's always area of the base times the height. Always. Talking about pistons in an engine, exactly the same thing. Everything's, every volume measurement. Figure out the area of one of the bases and then multiply it through by the height, and that will give you the volume of anything, which is fantastic. It's fantastic. So a cylinder or a box, whatever, is all the same. So we've got the area of the base now, 5 square inches. Now we multiply it by the height, which we said was 12, yes? So what does that end up being? The volume with this, the volume of that bottle, which I should give back to you now. I've got to put it away from you. You're enjoying it. The volume of that bottle is what?
60.
60 what?
60 square inches.
I'm hearing a lot of answers. Actually, I'm hearing 2 answers from a lot of people. So I got 60 square inches and I got 60 cubic inches. Why is it cubic? Remember, it's as Grant said, the area of the base times the height. So the area of the base, let's just do this in pieces. The area of the base times the height, right? We know the area of the base is 5 square inches. We know that already. And the height is 12 inches. Yes. 12 inches. When you have inches squared times inches, you get cubic inches, which hopefully makes sense because you have to fill the bottle with stuff. The base, the 5 square inches at the bottom is just a flat. You can't drink that. You can try it. There's nothing there. You have to then pass it up through the entire height of the bottle to actually get it filled with something, in this case, delicious water. All right? Make sense? Okay. 60 cubic, whoops, cubic inches. Beautiful. That's one bottle. How big's this room? You guys are adorable. 10-15. Master comes in and asks you questions like, how big's this room? Well, it's fairly large. we all fit in it. It's nice. give me some approximations. How big's the room?
20 by 30.
20 by, where'd you get that number from? Tell me your name again.
Guesstimate. And Randall.
Randall, thank you. Guesstimate. Give me a better, how'd you know? 30 by 20. I like that. Are you using your own height as a reference?
Well, my dad was a carpenter. He had to...
Awesome. So you have like a built-in measurement kind of default measure. That's fantastic. This is a very handy thing to have. My dad's an engineer. And so by default, I'm ruined mathematically because of what I think about. I think in terms of algebra and many, many things. Good. Go ahead. Behind you was
what if we assume that each towel is 1 foot and we count how many towels are across and then back?
A great trick. A great trick. What Randall said was great if you have kind of... There are other tricks you can use. For example, the height of the ceiling is probably to code in this building. Well, maybe. I don't know. It might not be. But I'm guessing it probably is code. I'm guessing it's probably, what, 9 feet or 10 feet to this. I'm guessing. I'm 6 feet. I'm roughly 6 feet. How much more above my head? Ish.
Probably like 9 feet. Yeah.
9 feet up? Oh, 9 feet to the concrete.
Yeah.
And then we've got a few more feet, maybe 3 more feet, 2.5, 3 to the ceiling. So we can keep that number on the back burner. But as far as getting the floor, look down. The tiles at this school, I think they got a package deal on them years ago. It seems like every room that was built in the 80s or the early 90s has these tiles in them. And they are 12 by 12. They are. So let's count them. They got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. That's damn close to 30.
And that's 25.
And that's 25. So since we have 27 by 25, let's actually use those numbers. So we got the volume of the bottle here. Let's slide the camera over. See, if you all just agreed with one number, I wouldn't be doing all this crap. So we got the volume of the room now. Okay? So that's going to be 27 feet. I think you said 27, right? I think I counted 27 across. 27 feet by, was it 25? We're going to ignore that corner. And we're going to ignore that space in the back, I think. We're gonna pretend that wall's just a straight shot wall. It makes life easy, and plus you can give and take, right? Some of this corner here will fill in part of that over there, not perfectly. Plus we're sitting in the room, we can pretend we filled part of that space too. By 25 feet. So what do we got now? How many dimensions do we now have?
675.
We've got 2. We've got a length and a width. We just need 1 more, don't we? We need a height, yes?
14 feet high.
14 feet! I like that. I like that. That's good. You think it's that high?
I said 12.
If I'm 6,
Yeah,
12.
and then we can ignore this little corner cut here. We'll just shove that back in that corner to make it a box. So what do you think? I'm 6.
I think so.
How much above me to the ceiling?
Like another 2.
12. I didn't bring my tape measure today. I usually bring it with me. I didn't bring it today. I apologize. We'll call it 12?
Yeah.
12 sounds code, and here's why does 12 sound code to me? Why does 12 sound code, do you think? It gives you, you're right, it gives you 10-foot ceilings plus 2 feet of wiggle room. They can install ceilings in if they need to drop them and run conduit and things like this. These buildings used to be this used to be the library before the Barber Library. So this has been retrofitted into classrooms. So it's going to be different than a lot of drop ceiling classrooms. Let's call it 12 feet. I think 12 feet, I think it's probably closer, just knowing that I'm 6 and knowing how much space is above me. So 12 feet. Okay. Let's get Google to help us out here again. Let's see if it can handle units. I don't know if I think they probably can. 27 feet times 25 feet times 12 feet. I spelled it right. Liters. Oh, it's giving me liters. I don't want that. Oh no, I don't want that. I just want this. There we go. 8,100 what?
Cubic feet.
Cubic feet. What the hell is a cubic foot?
One big foot.
Give me, a cubic foot is something I'm guessing we don't use in conversation. We got desks over here, guys, if you want to come over here. One here, one there.
Here's another one.
Yep, there's one back there if you want to head back there. Or just hang out there. Now we're getting into the danger area. I might have to start booting people out. Well, sit down then. Enjoy it. If it's comfy. So, everybody point to what? Do we have any? Okay. Well, we'll deal with waitlist in a second. We'll deal with. I got a print out here. We can deal with, get people in. Anyway, what is a cubic foot? Yes, symbolic. You a cubic foot. Look down at the tile, right, and then do what with the tile?
Build it.
Exactly. Build it up. Come up a foot. Put a lid on it. It's a box that's 12 inches by 12 inches by 12 inches. Yes.
Right.
So does that make sense? So each cubic foot is actually how many cubic inches? Because there's a problem with our measurement, right? This is in cubic inches, our bottle, but our room is in cubic feet. We have to convert one into the other to talk about it. And I think it might be easier to convert cubic feet into cubic inches than to convert cubic inches into cubic feet, because this is very small. And to convert it into cubic feet, we're going to have a .000 and a bunch of zeros. It might be easier to knock that one, bring that one up. Does that make sense to you guys? So, if that's 8,100 cubic feet, how many cubic inches are in a cubic foot? That's square inches in a square foot. No, that was great. We have to start with that, yes? And again, remember, I have an entire project devoted to this idea because of this, because of the discussion we're having right now, because it does. This is one of those wonderment questions. Like, I wonder, 80,000 bottles, is that meaningful? Let's find out. So 8,100 cubic feet, we have to convert that to cubic inches. Yes? There is, we can use Google to do it. We totally can use Google to do it. But I wanted you to get at least this one number in your head now, because cubic feet is something that might come up in conversation in your lives, believe it or not. So 144, well, there's 12 inches in a foot, yes? 12 inches in 1 foot. So if you look down at the floor again, look down at the floor again. 12 inches across one dimension. Also 12 inches across the perpendicular dimension. So if you were to go into that and draw little square inches, right? I wish you could see that. I'm drawing little square inches on it. If you draw little square inches on that, you'll have a row of 12 of them. 12 by 1, right?
Right.
And then a second row of 12, and then a second row of 12. Eventually, you'll have how many rows of 12 across? 12 rows of 12, or 144 square inches across the bottom. All right? 144 square inches across the bottom. Good so far? We're happy with that. Okay, now, if we build that up into a box, though, we can start by building 1 inch up. We're still going to have 144 little 1-inch boxes, yes? Then if we add a second layer, I wish I had brought props, I apologize. I didn't think we were going to do this today. If we then put a second layer of blocks on, there's 144 more of them. So that's 288 at this point, yes? And if we put a third layer of blocks, it'll be 144 more. It's 144 times 12, which, if I remember correctly, and don't trust me on this, I think it's 1,728 cubic inches. It's one of those numbers I have ingrained in my head from my dad, the engineer. Thanks, Dave. So, to convert cubic feet to cubic inches, all we've got to remember is, for every cubic foot, there are 1,728 cubic inches. So we take that times that, and that tells us how many cubic inches are in this room. Fair enough? Anybody not care anymore? Possible. Possible. Great. Love this. Love this. It's called street fighting mathematics. Just figuring out stuff on the fly. Let's back this up a little bit. Okay, so now 8,100 times. Actually, I think we can do this. 8,100 cubic feet in cubic. Did I spell it right? Inches? There we go. About 14. Let's call it 14 million. We're rounding everything else off. And that's damn close to 14 million, isn't it? Yeah. To do that. It's damn close, 14 million. 14 million cubic inches! Surprise, look! I love that. Does it seem like more than you thought it was? It's just 10:50, 10:30, it's way too early to do this kind of crap on the first day of class. My God, I heard you were crazy. So 14 million cubic inches. Now hopefully the magnitude of the number makes kind of sense. You've got 8 times 10 cubed here, and you've got 1 times 10 cubed here, roughly 2 times 10 cubed. So you're going to have 10 cubed times 10 cubed, which is 10 to the 6th power. Sorry, scientific notation. That's really not a cool thing to be doing at 10:30 in the morning. But as far as scale-wise, that number of zeros makes me happy. So the volume of a room is 14 million cubic inches. 14 million cubic inches. Good. Good! So how many bottles would fit in this room? How many bottles would fit in this room? Why don't we just take the 14 million and divide it by the 60? No, we don't like that?
60 into the...
Oh, sure. I think we said the same thing, potato, but take that, divide it by that.
Yeah.
Yeah, and tell me your name back there.
Me?
Yes.
Haley.
Haley. You don't like that? Oh, you already did it!
I just did.
I love smartphones. Fantastic.
Oh, yeah.
Go ahead. Give me Haley.
233,000.
233,000. What?
Bottles.
Bottles! I don't think we're really wrong. I don't think we're... We said they would fit in the room. We just proved they would. But it looks like they won't even fill roughly half. Now time out. We're being a little bit illegal here by saying that. Now why? When we divided that 14 million cubic inches by that 60 cubic inches, that was we're actually doing, it's a little bit illegal. Hold up the bottle again if you don't mind so we can see the shape of it. What shape is that bottle? It's a cylinder, and if we start stacking these bottles in, can I borrow some cylinders if that's okay with you guys? If we start stacking these cylinders in,
You're losing volume.
you see there's space between them. There's going to be space between them. They won't fit like this. This is all the air in the room. There's 14 million cubic inches of air. That's all just kind of melding together.
So if we smash the bottles, we could probably fit them in there.
Yes, let me show you these back everybody correctly. If we smash the bottles, if we dump the water into the room, then the bottle argument is gone, yes?
Yes.
I mean, we can forget about the bottle argument. But that would also be messy, and you could get your water back, especially if you have like your favorite chai in your little blue bottle. Well, we could also just assume that we know that that divided into that is about 233,000 bottles, but that's too many, so you might make an adjustment to that and say, okay, that's assuming that the bottles fit completely tightly. I'm going to let this go because you guys, I sense there's a loss of interest in this problem now. But you could also figure it out if you took some cylinders that were all shaped like the bottle of interest. You could actually mathematically get in there and figure out how much space is wasted.
It's dripping.
Right? It's dripping. Sorry. I thought you said it's true. I'm like, she's with me. Like, no, she said it's dripping. It is.
Yeah,
It smells lovely. So you could figure out mathematically using some more geometry how much space is wasted, and then you could get a more refined estimate. But you know, honestly, that got us in the ballpark, didn't it? It's surprising how many of those bottles would fit in this room, even if that estimate was off by a factor of 2, which it's not. It's not off by a factor of 2. We could still fit all the bottles that we've saved on this campus for the past 2 years in this room with room to spare, probably for us to sit around them and enjoy them, yes? And then have to make frequent restroom breaks to go clear out the extra water. So, does that make sense? That's the kind of math you never learn in algebra classes. Doesn't that annoy you? Isn't that annoying? The kind of math, I mean, that kind of math. How to visualize that number that I've erased. Oh, that's 6,477 bottles. It's a great little statistic dropped on you right there in the, right there. Every time you fill your bottle up, it changes probably by 1, yeah? What does that mean? Does it mean something? Yeah, it does mean something. We just figured out something that it meant. We just figured out that if we took all the bottles that were saved and put them into this room, we'd have room to spare. That might not seem as impressive anymore, huh? That might not seem as impressive anymore. It's like, great, thanks for ruining my day.
It's kind of neat though that you can, get all this from life and see it on paper, So all the other algebraic stuff, you're like, what are all these numbers?
It's all useful. Tell me your name too.
Francis.
Francis, thank you. Thank you for succinctly saying exactly what I'm getting at here. We're going to build on what you guys have learned your entire lives, but hopefully show you a side of it that you've never explored before. Because it's all good. It's all good. I think sometimes the cart leads the horse, though. I actually heard a guy from U of O say that every algebra student is being programmed to take partial differential equations. Every time you sit into an algebra class, whether you took Math 60 here, Math 65, Math 95, I'm guessing you guys just took Math 95, yeah? A bunch of you guys. All those courses are designed to get you into a calculus course. How many of you are done after this course? This is your last math course. Yes, good. How many of you taken Stat 243? Couple, good. That's what I like to see. I've designed this course kind of with that in mind. I wanted to kind of point you guys. And then 244, some of you after 243, a couple of you. Good couple of you. Who's taking other stuff besides what I just mentioned? Go ahead.
I don't know what the course numbers are, but I'm taking every math class that's offered.
Bless you, son. That's awesome. That's fantastic. We're just going to say 1-0 blah. Just go from there. And 2-0 blah. Very, very good. And that's Michael? Aaron. Randall. Where was Michael? I talked to Michael earlier. Nope, I didn't. That's in my head. Whew. Okay. I ask you to repeat your names a lot because of that. Whew, man. Yeah. The older I get, the worse it gets. Yeah. So, Francis, thank you. That was a very succinct, what you learned was not useless, but a lot of it was fast. A lot of it was, I'm kind of in the belief that you should learn stuff just in time. Like when you need something, we learn it kind of there. Grant, you brought us back down memory lane today with that volume calculation. Thank you for that. Now, chances are you all learned that when you were like 14, 15 years old. I'm guessing. You sat in a geometry class and you suffered through a volume calculation. And it's freaking awesome. It's totally awesome. It's why they pack trucks the way they pack trucks. If they want to save resources, they use those kinds of calculations. It's why your grocer, when they stack apples and oranges, they stack them in those little nested things. A, it looks nice, but B, it's the most mathematically efficient way of stacking things. I mean, it's just the way it is. It's why Pez sits the way it does in a Pez dispenser. My son loves that one. So, the math you learned is fantastic, and there are wonderful tools in the math you learned. I just want to take it past that and show you how it all links together in other ways. I mean, you saw dimensional analysis today, you saw some geometry, you saw a little tiny bit of arithmetic. Dimensional analysis, I think, is what really drives students nuts because they're not used to it. Very often in algebra classes, solve for x, x equals 3, solve for this, solve for this, solve for this, and that's all it becomes is solve for this. So we'll take you past that hopefully here. We'll do some solving, of course, because it's important, but also I want to take you past that and take you into other places like how many bottles fit in the room. That was fantastic. Good? Welcome. You're all still here. I didn't scare anybody off yet. We'll take 5 halfway through though, and we'll the class is long. I mean, 2-hour class is a long time to sit in here and talk about mathematics. So usually I take a break at 11, kick you guys out for 5 minutes, flush some fresh air into the 14 million cubic inches that we have, replenish some of the carbon dioxide with oxygen, bring you back in, let you move around a little bit, and so forth and so on. So anyway, welcome to Math 105. I'm Sean. Didn't introduce myself. Hit you with a bunch of math first. Apologies. Apologies. I did mention that we do record classes. I'm going to start